The RTO instruction, the retentive on-delay timer instruction. We've already at depth discussed the TON and the TOF, the on-delay timer and the off-delay timer. And I remind you again that there is only one timer data type that's made up of a preset accumulate and then a word with some control bits in it and the time base. This particular processor supports 1 second, 100th of a second, and 1,000th of a second. Now typically, these days I always use 1,000ths of a second simply because when you get to RS Logix 5000, Control Logix, Compact Logix, those timer data types only have one time base. This particular processor does not have double integers, 32-bit words. It's all 16-bit words. So with signed integer, that means that the bit 15 or the 16th bit represents the sign of the number, whether it's positive or negative. That leaves you 15 bits total to actually define your integer values. So you have minus 32,768 all the way up through 0 to plus 32,767. However, with the Logix engine in the newer platform, you have 32-bit words. So if you use 1 bit for your sign, that leaves you 31 bits. That's a big number. With the older processors, you had to have the longer, if you want to call them that, time bases of 1 second. So you could at least get up to 32,000 seconds if that's what you needed. Well, when you have 32 bits for your timer data types, you could use 1,000th of a second and no problem getting up to 32,000 seconds. There is only one timer base. The instructions are what makes the difference. How the instructions address that timer, that instance of a timer data type. In this case, we've kind of stuck with T4:0. It's just a habit from days gone by to use the lowest unused element of the array. So T4:0, we'll go over here and double click on it. And you see that we have it expanded out to 10 elements, T4:0 through T4:9. And it can be expanded out, not online. You can't do it here. See, this is all grayed out. You can't expand the data table online. But this could be 255 or 256 elements, 0 through 255. So it's a habit to use the lowest numerical value in the array that's unused. Since there are no timers used but one here, we use T4:0. Well, guess what? In the newer platform, there is no numerical array for timer data types. You can name it anything you want. You can name it monkey doings, and that's the name of your timer, the instance of your timer data type. Well, that doesn't get stored anywhere numerically that you're aware of. You'll see that when you get to the newer platform. But for right now, we are working with pre-declared variables. T4 is a pre-declared timer data type file. T designates timer data type, 4 is the file number. So this is pre-declared for you. When you created your project, you didn't create B3, T4, C5, R6, N7, and F8. They were created for you. So therefore, they are pre-declared variables. Now you can expand your data files. You can expand each of the default ones, B3, T4, C5, R6, N7, F8, out to a total of 256 elements per file. And you can also create a file 9 of any of the data types that are available with this controller. And you can have file numbers all the way up to 255. So you could have B255. You could have N254. It doesn't matter what order they're in. So don't be confused into thinking that it has to be B, T, C, R, N, F in that order. These, by default, it's created for you. They're pre-declared for you. Now, when you add a new file number, then you are following the pattern that they gave you for pre-declaring data files, therefore pre-declaring the variables or the pointers. Okay, so T4:0 is a pointer that points to a timer data type somewhere in memory. TON, TOF, RTO, they all address identical timer data types. The difference is that a TON, when the run goes true, it enables the timer, the time base that was configured, to start incrementing or accumulating units of time until the accumulate equals the preset. During that accumulation time, the timer timing bit is on, and when it's done, it's no longer timing. That bit goes off and the done bit comes on. Now the TOF was quite a bit different in that it really doesn't start timing until the run goes false. So it's delaying off if you compare the condition that enables the timer to the memory location that responds to the done bit. The RTO is really identical to the TON, with the exception that an RTO has no false execution. Just like the latch and unlatch, they don't have false executions, where the OTE does. And we have two of them right here on our screen addressing output 0 and output 2. Those are OTEs. If the rung's true, it turns the bit on. If the rung's false, it turns it off. With latch and unlatch, if the rung's true, the latch latches a bit. If the rung's false, it doesn't do anything. The unlatch, if the rung's true, it sets the bit to 0. If the rung's false, it does nothing. An RTO is a TON timer. It's a retentive on-delay timer. And the way they make that happen is it has no false execution. If I turn on input 0 here, and by the way, I just noticed something. This timer was already done because I went in and changed the instruction type from TON to RTO, but I did not do anything with the values in the preset and accumulate. I left them the way they were. So if I had converted this from a false rung, the accumulate would be set to 0. That's a good thing that's happened. I'll just go in and put in a 0. And this is part of the lab. It's not enabled, but it's still done. So I'm going to have to go to the timer database here. And look, T41. That was left enabled and done. We're not even using T41. It's not anywhere in our program. This is data table carnage, and this typically only happens when you are using the same processor to do a variety of things, and you stop a program right while it's running and then go offline and then create a new program and download over the top of it. If your new program doesn't address those data table values, then they don't change. The last thing they heard was you're on. Okay, so this is how we want to start. If I push that button, input 0, and let go, I was able to press the button fast enough to get 0.08 of a second time of pushing the button down. This timer instruction is going to enable this timer data type anytime the rung is true. I'll do that one more time. That time I had 0.06 of a second. There's no false execution, so this behaves just like the TON, with exception that when the rung goes false, it doesn't clear anything. It just stays right where you left it. The last thing it heard was increment or accumulate. Now, while you've got the button pushed down or on, it is enabled and the timer timing bit is on. See? Timer timing bit's on. If I hold it down long enough, push it often enough, then the done bit comes on. So it behaves just like the TON, except there's no false execution. While input 0 was on, did any of the outputs energize? Yes. Which ones? Enable and timer timing, because you enabled it and the timer's timing. Does flipping input 0 on and off affect any change once the done bit is set? Well, the done bit's set right now, right? There's your answer right there. It has no effect on anything, because the RTO cannot instruct that memory location, that timer data type, to accumulate past the preset. So it's not timing, And it's right now it's not enabled and it's not timing. Right now it's enabled, but it's not timing simply because the accumulate equals the preset. So if you have trouble remembering how an RTO works, it works just like a TON, except it has no false execution. So everything that you would expect to happen with a TON when the run goes false is not going to happen with an RTO. And there's an advantage to that. Does the timer instruction reset the timer in the data table when the run goes false? No. Did the timer resume its accumulation now that the accumulate does not equal the preset? So I had you go in and you could do it here. I had you go right into the data table and change the accumulate to 0 by just clicking on it, 0, enter. You could have done the same thing right here. You could have clicked on it here and typed in, did the timer resume its accumulation now that the accumulate does not equal the preset? No, when this thing's done, it's done. You have to clear the done bit. Then I had you type in a 0 for the done bit. You can't clear it here. You can't click here. You have to go right into the database, hit 0 and enter. Now, I had you do these things with the input on, so I just did them with the input off, so I'll lock this on top, just so we don't have to open it again. Clamps it down, because we only care about T40. And then I'm going to go in, I'm going to flip that input on and let it time out, so the done bit's on. Because instructions did say with input 0 on, open T4 file, lock it on top, go to the accumulate, and it did not start timing again. Then go to the done bit, hit 0, and it does. The only reason it didn't with it off, I'll turn it off, and I'll click here, and then I have to go here to do this one. It doesn't start timing again because the rung's not true. If the rung were true, it would have. Now, this was tricky. I had you increase the preset to 1,000. Actually, I had you do that at the beginning of this lab. So I'm going to go set the preset. I can do it here or I can do it here. I'll click there. This is another thing to observe. It's done, right? And the preset and the accumulator are equal. I'm going to make that 1,000, hit enter. Now they're not equal. Does it start accumulating again? No. That's because when it's done, it's done. Now if I set this to 0, again, the preset and the accumulator aren't equal, but it's not going to start timing again until you clear the done bit. So I'll clear the done bit. Now it starts timing again. Now the reason I bumped it up to 1,000, which would be 10 seconds, is to give you time to do what I'm going to have you do next. And that is, I'm going to clear the accumulate, and I'm going to clear the done bit, and let it start timing again, but then I'm going to set the done bit. So 0, enter, 1, enter. Okay? So I set the done bit before the accumulate equal the preset. So when it's done, it's done. The done bit dominates the timer data type. If it's done, it's done. And you know, you can manipulate the value in the preset and the accumulate from other instructions. I mean, on the fly, while you're running the program, you can use an instruction that changes the preset in that timer and changes the accumulate. Now, I'm not going to give you any reasons that you should be doing that, because that's at best awkward to understand logic for someone that's trying to troubleshoot it, and it's at least convoluted. And when you're writing programs, you never want to create convoluted logic that only you understand, and you had a little hard time understanding it yourself, and then you put it out in the field, and some poor person, maintenance person, at 2 o'clock in the morning, the machine's down, and he's looking at your logic and going, what the? Don't do that. So stay away from convoluted logic. Try setting the done bit before the accumulate equal the preset. What happened was done. It stopped accumulating. Will the timer continue to accumulate if you cycle the switch 0 off and on again? This is not exactly the same values. In the manual, I think it had, I don't know, 219 or something, but whatever. I'm going to turn off the switch and turn it back on. You see, nothing happens. When it's done, it's done. If the done bit's set, it's not going to do anything. You're going to have to reset it. And of course, you could create your own kludgy reset using a clear instruction and using an unlatched bit, which we do later on. So the timer did not continue to accumulate when you turn this switch input 0 on and off again. Another thing that we had you do is we altered the done bit to get it to start timing again. Turning off the done bit will get it timing again. And we know that it's done if the accumulate equals the preset. Let's reset all this. Turn off the input. We can right click here because I have the done bit exposed. I can toggle it. We'll leave it right there. Okay? Start this up again and then change the preset to something less than the accumulate. So I'm going to have to do this real quick. Okay, I was able to type in a preset lower than what the accumulate was on the fly, and it immediately stopped. Because remember that the timer data type, if it's incrementing, accumulating, and the accum is equal to or greater than the preset, it's going to stop, as you see right here. Now I'm manipulating these values from my keyboard, but you could manipulate these values right in your logic. In the first instance is right in front of you. I see that in the manual I had misspelt pseudo. I corrected it here. I just happened to notice that. So you may have a copy of the manual that has pseudo misspelled UE instead of EU. Nonetheless, we created a pseudo reset. This exactly as it is. I'm going to do this with it enabled. So right now it's enabled. It's done. So I'm going to push the pseudo reset button. Notice that it clears everything. As long as I hold down the button, I'm still executing rung 3. Over 1,000 times a second, it's going clear the accumulate, undo the done bit. If I let go, then it runs again. So if I hit the reset, my pseudo reset, down there, and I turn off input 0, it's not done, it's not timing, it's not enabled. If I hit the reset button, watch the accumulate value. It clears it. These are all behaviors that you need to understand, because I'll guarantee you that people will use these 3 timer instructions and the timer data type for anything they can think of that solves the problem at hand, that accomplishes the logic and the results that they want. You have to be able to look at their logic and recognize what it is they're doing with the timer data types. I had you reset the timer before it timed out. Will a reset instruction reset a timer only when it is done, or at any time? Any time. If you execute the reset instruction while a timer is timing, what happens? Resets and starts over. Now in the manual, I did have you put in a reset instruction with a different input so you could see the difference. I'll do that real quick. Okay, I added, I know it says 1PE. That's because I did not delete the database. So I will just delete that so there's no confusion. In the manual, it's also was 1PE. Timed it out and I went false on rung 0, but it's done and the preset equals the accumulate. If I hit my pseudo reset, input 1, that clears the accumulate value and unlatches the done bit. Now remember, it's the unlatch instruction. Don't think that that implies that the bit was latched, because it wasn't. It was set. The latch instruction sets the bit to 1. The unlatch instruction sets it to 0. With an OTE, true rung sets it to 1. False rung sets it to 0. So latch and unlatch are terms that kind of came from the relay world, but they're still usable. So we did not latch this bit. It was set to 1, but I'm going to use the unlatch instruction to clear it. So if I push the pseudo reset, it clears it. And I can do the same thing with the real reset instruction on input 2. So this illustrates the behavior of the RTO instruction. It has a true execution, no false execution, and it also compares the reset instruction, which is what you're going to use. You're not going to clear and unlatch the done bit. But I did it this way so you could fully understand what the reset instruction does. And by the way, you can use the reset instruction for any timer instance of a timer data type, whether it's being instructed by a TON, TOF, or RTO. A timer data type is a timer data type. The reset instruction doesn't know what kind of instruction was addressing that timer data type. It just clears it. Consequently, and we didn't do this in lab because there is no valuable reason for doing it, but you could address one instance of a timer data type, like T4:0. You could address it with as many timer instructions as you like. Not only multiple TONs and TOFs and RTOs, but combinations thereof. That wouldn't be very smart. You could do it just for fun on your own time to see what kind of erratic behavior that you would get.